Welcome viewers. This is stage 3 of design of 220 kV double circuit transmission line tower in robot structural analysis in Indian standard. In this we are going to look about the connection design. You can see an Excel sheet in the left hand side which is developed to demonstrate this connection design, and also you can see a PDF file in right hand side IS 802 part 1 section 2, which is having a table 1 showing the ultimate stress in bolts for both the grade 4.6 and 5.6 in the unit of megapascal. So here you can see that the shear strength value, bearing strength and axial tensile stress. So similar like we are also having in our Excel calculation the same value according to the selection of grade. This will vary. So we can consider the 5.6 grade of bolt for our calculation. So that the shear value are extracted directly from this table using a separate table updated here, added here. You can see that the shear value of this calculation, Excel calculation, is having 310 megapascal for 5.6 grade, and similar like bearing stress is 620 megapascal, axial tensile stress is 250 megapascal. So once after finding this stress value as per the IS 802 part 1 section 2, the table 1, now we need to calculate the load carrying capacity of bolt in shear, bearing and axial tensile stresses. So we know that the stresses, if you multiplied with the stress area, we will be getting the force. So we need the area of stress area of each cases like shear, bearing and tension. So for that 802 part 1 2 had given the definition how to calculate the area under shear and bearing. So you can see in the right hand side it is mentioned 10.4 for shear stress and 10.5 to be referred for bearing. So for that page number 6 to be referred. So here you can see 10.4 is a cross area of bolt is stating that the purpose of calculating the shear stress, the cross area of bolts shall be taken as the nominal area of the bolt. So simply we need to multiply, we need to find the area of a circular, because this bolt is in a circular shape, so we need to consider by d square by 4 where the diameter is a nominal diameter of the bolt. And in case of bearing calculation, the bolt area of the bearing shall be taken as d into t, where d is the nominal diameter of the bolt and t is the thickness of the thinner of the parts joined. So here in the Excel sheet you can see that the diameter of the bolt into thickness of thinner member we need to consider to calculate the bearing area. Next is the tension area. So for tension area it is given that in 10.6 the net area of a bolt in tension shall be taken as the area at the root of the thread. So only the threaded diameter to be considered. So here again for the circular portion we need to consider by d square by 4. Here the d, the diameter is a threaded diameter. But in our transmission line tower design or connection design, this tension, axial tension stress and the tension area or the tension force is not required, because our entire bracing system is like a lattice, that is a web based structure. All the members used to transfer only the axial forces, so there is no bending stresses or bending moment to be transferred to the bolt. So in that case we can simply ignore this axial tensile stress or tension area or its tension forces. So this calculation is not applicable for us, because this is applicable only for the moment connection. Moment connection where if there is a 4 bolt which are fixed to a member subject to a moment, if the movement is acting in this direction, the member which are hold by the other two bolts are subject to tension. In the other case, in the other direction, bolt will subject to compression. In order to make the equilibrium stage to the resultant moment, this will happen. So only for the moment connection we need to check for the tensile stresses. For our transmission line tower, we need to consider only the bearing stress and the shear stress. Also, there are two methods of shear stress which are applicable for our transmission line tower. One is a single shear, another one is a double shear. It is nothing but single shear means we need to multiply this shear stress 310 megapascal with the shear area pi d square by 4. Double shear means we need to multiply with 2 into shear stress 310 megapascal into pi d square by 4 of bolt. So that is what. So where we need to apply this single shear and double shear is for all the leg member which are subject to butt type of joint. It is not a lap joint, it is a butt joint. We need to consider only the double shear. Remaining for bracing, we need to consider single shear. Why it is? Because the bracing will have one directional force. So the resultant shear will be in one direction. So it is, we need to consider only the one single shear resistance. And in case of a butt joint, there is a two-way shear because we are going to make the connection, splice connection in both the side. The angle member is used to have a connection in both the side, both the flanges, so that it will cause double shear. So we need to consider only the double shear resistant in case of leg members which are subject to splice connection. So now next we will go into that detailed analysis of connection. So for better understanding of the connections, there are some pictures or photos which is kept in the right hand side. So this first two photos is for a splice connection between the main leg member. So here you can see in the left hand side picture one angle which is smaller than the other two main legs which are connecting are kept inside, whereas the bolts are staggered in connection. The second photos picture which is in the right hand side is a outer face of the main leg members, whereas you can see two plates in two faces which are having same number of bolts with the staggered arrangement. So in the upside you can see there are 4 plus 4. In the side view you can see 4 plus 4. So these are the same in and out of the main leg member splicing. So next we can look into that bracing bolts. So this kind of bracing is having a 2 number of bolt connection. So if the 2 number of bolt is unable to accommodate with the main leg members, if the flange is less than to accommodate the 2 number of bolts from the bracing, we need to provide a flat plate called a gusset plate, so that this gusset plate should connect to main leg and projected a little bit outside to connect the bracing, so that these two bolt which is required for the bracing member to withstand its force can be accommodated with the gusset plate and connected with the main leg member. So this picture is another view of this two bolted bracing member which cannot be accommodated with the main leg members. And in the middle you can see one single bolt which is provided to break the unsupported length of the bracing. And the last picture is about the single bolt are single bolted bracing members. Here one bracing member is connected in the top, another one is at the bottom. Now let me look into that calculation with this understanding. As we know that for leg members which are having a double shear resistant, you can see in this picture the main leg members are connected in two phases. So suppose if you are taking this member alone, it is connected in two phases, this side with the plate and bolt, again this side also with the plate and bolt, and in the inner side we are keeping the angle members. So that is why we are telling that double shear resistance are applicable for main leg members, but in here only one flange is fitted in that bracing member with the bolt, so only single shear is applicable for bracing member. So this member group we can pick from the slenderness calculation. So we can directly link this by simply pressing equal and drag this up to the end. So likewise we need to do it for leg bracing type also. We are already having this member type in slenderness calculation. So similar like profile size we need to pick from this slenderness. So next for the diameter of bolt we can fix M16 for all. Later we can change according to that usage and the result. Coming to that number of bolts we can consider as per our assumptions initially. So for example for main leg up to the body we can have it as a 6 numbers of splice connections or bolts, and the remaining for primary bracing we can keep it as 2 number of bolt per member, and for secondary bracings we can have a 1 number. For other legs such as the leg of cage, peak and the cross arm we can have it as 4 numbers. So let me look into that how this calculation is going to work. So all this blue color text are the input value or variable value we need to feed here. So if you are selecting here as a leg member, then this joint type will select as butt, and for the other bracing members there is no need to mention any joint type here, and this member thickness will capture according to the profile size based upon the Excel table here listed, and this gross area is nothing but by d square by 4 which we had defined here, and maximum compression or tension force we need to extract from our robot structural model which we got calculated already. Bear resistant bearing capacity of the bolt we need to calculate as per the formula described here in IS 802 part 1 section 2. So we state that diameter of the bolt into thickness of the thinner member to be multiplied. So here in this case for splicing connections, as there are 2 members to be connected, so we need to check which one is a thinner one. As of here the leg member 1 and 2 are same kind of member, so we no need to bother about it, or else we can drag this little bit down for the member thickness alone and press enter. So this is what the bearing calculation. Next one is a single shear which is not applicable for main leg or leg member which are having a splice connection where both the flanges are connected, so there must be a double shear alone. So we need to calculate the double shear. So for double shear, if it is a butt, it is a double shear is applicable. So here 2 into, and as per this grade The stress value for shear is 310 megapascal, which is extracted from this table which we had discussed earlier. Accordingly, it should be multiplied with pi d square by 4, which is a cross area here. So then we will be getting the double shear. So 310 into 2 into cross area 201.06, we will be getting 124.65. So this is applicable for all the leg member, and for bracing we need to multiply it with this shear capacity 310 megapascal into cross area 201. So with that we will be getting 62.31 kilonewton as a shear force. And here the minimum capacity is considered with the bearing capacity, single shear or double shear capacity, and finally this minimum capacity resistant is checking with the actual compression or tension forces. Then the usage is like actual divided by the capacity into 100 will have the usage in percentage. So if the percentage is less than 100%, then this connection seems to be safe. So this is a calculation procedure. Now we need to get these member forces from robot structural analysis. We already fixed this all. So these are the value directly we had extracted from that robot structural analysis. So how to extract that force is first to go to the results. So before that you need to check that results FEM available nodes should be represented in green color so that the analysis is available, the results are available. Now go to that results, click forces, always select these combinations in the load list, and here we need to select as per the leg member group 1. So if you select it, you need to press this double time so that it will show you the maximum and minimum value. We need to get only the absolute. We need to consider that absolute value, even though it is in minus or positive, we need to check the numerical values, which one is maximum. So here 530, that positive integer is higher, so we need to consider this 530.47 here. So similarly, like we need to check for other leg members 526.03. So likewise for all the group member we can extract the maximum force value, and we need to enter here in this tabulation. Here that CABB value is very lower, 0.61 only. So likewise we need to extract for all the group members. Here that hip members XHB, YHB, for this we can consider the exact value of nearby bracing with 1/3 of the loads. We no need to consider the full load, and with that 1/3 we can fix how many number of poles is going to come. Maximum it will be only one number of pole. So after filling all this force value, let we see what it is happen in our usage or result. So all the results are safe. We can also optimize this connections. So here the number of poles, if you see here for leg member at the body, it is having a 71% and 74%. So this we can't able to do anything, but here up to this bracing member we can do some optimization, because those values there, those usage factors is less than 50%, so we can have it as a single bolt bracing. Now coming to that leg, so this is already 82%, so no need to do any changes here. And hip bracing anyway we can consider one number. So for this leg member we should always have at least 2 number of bracings. So this is peak level leg, and here the bracing are also having less than 50%, so we can have it one number of bolts. Again this is leg member, so we can have it 2. One. So with the one number of bolts all the bracings are safe. Even this bracing is having some 97%. If you see, if you are worrying about this edge or nearer to that 100%, you can have it 2 number of bolts, that's not a problem. So likewise we need to do our connection design. So with this the connection design is end. With this stage 3 get completed, and all the technical discussion related to the design of 220 kV transmission line tower as per IS 802 get completed. So next video we will be looking on the foundation design. Thank you for watching. Look description for more related video. Subscribe to this channel for more updates. Thank you.